Good morning. Stay online while we wait for your classmates to join. Okay, people are starting to join. Please hold. Okay. Where is the progression calendar? Nice. Today is 12. Okay, I think we are done with the heat transfer topic. Only thing remaining is evaporation. And then we can comfortably go into light.
Good morning, sir.
Good morning.
Sir, I'm a new student.
Sorry?
Sir, I'm a new student.
Oh, yes, Kevin. Okay. Yeah. I've been informed that you are. What now? In the past couple of months, did you attend were you in a previous school attending online class or something?
No, sir.
Okay. We are going to have a bit of an issue now. Now, in your previous school, did you study about energy and thermal energy? Kevin?
I think no, sir. Sir, in last school, physics and chemistry was not there.
So the previous term also, you were not in school?
No, sir. I joined yesterday.
No. Not in CIS. I'm saying your previous school. You didn't attend classes for the last term?
Sir, I have attended.
Okay. And now last term we covered forces and motion. So that means velocity time graphs, distance time graphs, then balanced and unbalanced forces, and moments. So
Sir, these things were not there in last term.
but then what are we going to do about those topics?
Mm,
Sorry. Sorry. Hold on. Problem is
Sir, what is the syllabus of this term?
the syllabus of this term. Now, up to now, we have covered energy, energy stores and transfers, then Sankey diagrams, then thermal energy. So anyway, you just stick around for today's lesson. I'll figure out with the secondary office what to do about your missed work.
Okay, sir.
All right. I think we can start now. So today we'll be finishing up thermal energy with the topic of evaporation. Right. Now, up to now we have studied about conduction, convection, and radiation. So conduction is the transfer of heat by vibration of molecules, and in the hotter part, the molecules are vibrating much faster. So they end up, this vibration is passed from particle to particle, and it goes through the material. But metals are especially good because of their free electrons, especially good at conducting heat. In convection, we learn that it's the upward motion of less dense fluids. So when a fluid is heated, it expands, and when it expands, it becomes less dense because the mass is being spread over a larger volume. So the less dense fluid will rise. And then radiation is through infrared waves. Oh, now, Kevin, we have videos. We have videos of these lessons. So I can...
Okay, sir. Recording?
Yeah, recorded videos. So I can set you up with the videos. Yeah.
Okay, sir.
That's what I'll do. I'll just make sure that everything you need is there. And then I'll email you through the GC. Okay. So today our topic...
Okay, sir.
All right. Today our topic is evaporation. Evaporation. Right. Yeah. So evaporation is a strange process. Now it's very different from boiling. When a fluid boils, by fluid I mean, sorry, when a liquid boils, the bubbles are there all over the liquid, yes? So first let's highlight the difference between boiling and evaporation. If it's boiling, these are not particles, these are just bubbles. Huh? So this is boiling. In boiling, the liquid changes to gas throughout the liquid, and boiling only happens at boiling point, right? So liquid converting to gas all over the liquid. Then also it happens at boiling point. On the other hand, so And also heating is required, no? Heating is required. On the other hand, evaporation, now let's say that's what happens. Actually, evaporation is what happens when if you spill some water on the floor, then the next day you come back and the water is gone, even though the temperature is room temperature. So on the other hand, evaporation, here this part is not very visible, no? Because my ink is kind of messed up. Hold on, I'll see whether this works. It's permanent. Heating required, liquid converting to gas all over the liquid, and it happens at boiling point. Hold on, rest of it, now the rest of it I'm going to write on MS Paint. I'm going to share the screen and do it because this is not very clear. Hold on. All right. Please write this down and let me know if you are. I'm going to erase it in like a minute. So these ones are heating required, the liquid converting to gas all over the liquid, everywhere. Then it happens at boiling point. Now, you guys know the boiling point for water. 100 degrees Celsius for water. For ethanol, it's 70 degrees Celsius. Then, different liquids evaporate, boil at different temperatures. Boil. Right? Is anyone still writing?
Sounds good.
How about now?
So could you keep the last bit that happens at the...
I can't hear. What is it? Could you?
Could you keep the last bit?
This one. Happens at boiling point.
Last.
Happens at boiling point and it's 100 degrees Celsius for water. Okay. Okay, now we are just going to switch to the screen here. All right. No need for video. All right. Now, evaporation, on the other hand, happens at the surface. Wait, we need the paintbrush now. There we go. On the other hand, evaporation does not need a heat source. So, can you see this, or do I need to increase the brush size? Probably, eh? All right. So evaporation happens only at the surface. So now this, you have to remember that the particles here are all moving randomly, and they have different amounts of energy, right? So some are more energetic, some are less energetic. Just like, you know, in a classroom, there's average energy, you know? There's like kind of an average attitude, average energy. But within that thing, there are low energy people and high energy people. So similarly, for the liquids also, these particles that I've drawn, they're moving around, but some of them have more energy than others. Yes, Arvin, any question?
Sorry, I'm late, sir. There was a problem with my Wi-Fi and I had to reset it.
Okay, now you missed something. Hold on. We are discussing evaporation, and I first highlighted the difference between boiling and evaporation. Boiling is when the liquid is changing to gas all over the liquid, everywhere, right? And it requires heat, and this boiling happens at boiling point at that specific temperature, right? So leave space for that. Then let's continue. Now, with evaporation, on the other hand, the actual interesting part happens here at the surface. Oops. At the surface, there's some special stuff happening. So the high energy particles, now these are the particles just, randomly moving around. But then a really energetic particle at the top may gain enough energy to escape the surface, right? This one gets leaves. So then I'm just going to label some here. This is a problem with computers, huh? Hold on, seriously, why is it not responding? Okay, finally. Right. So low energy particles remain within the liquid, and high energy particles can escape. Now, compared to boiling, now let's write something about evaporation. Okay, within the same liquid, different particles have different energies. That's the first thing. The most energetic particles reach the top and escape into the air. If it has enough energy to escape, basically, right? So unlike boiling, which happens throughout the liquid, evaporation happens at the surface, and surface needs to be boiled, right? At the surface. All right. There's another thing. Now, evaporation can happen at any temperature, right? It's not like boiling. Boiling happens at one temperature called boiling point, but evaporation can happen. Oops. No need to bold that. Okay. Hold on. Evaporation can happen at any temperature while boiling. Requires a specific temperature known as let's just I'm just going to put it here, okay, so that it's visible. Within the same liquid, different particles have different energies. The most energetic particles reach the top and escape if it has enough energy to do so. Okay, please write that down. Hold on, I'm just moving this to my okay.
Sir, this is not in the book, right?
This is not in no, this is not in the book. All right. Anyone still writing? Please let me know which part you are writing currently.
So I'm still writing all the points starting from within the same liquid.
Take your time and write. Okay, now is everyone done with writing?
Sir, not yet.
Not yet.
So I'm on the last point.
My God. Okay. No, we are comfortably ahead of syllabus. And today I was thinking of transitioning on to light, but I think for the benefit of, no, we could discuss, the most recent topic of heat energy. right? Still writing? Everyone's done, no? All right. Now, what are the factors which affect the rate of evaporation? So you have to think, right? Imagine if you leave water in a bottle. Okay, where are we? Imagine if you leave water in a bottle and keep it in a room. Next day when you come back, most of it's still going to be there. Just a little bit would have evaporated, no? On the other hand, if you take that bottle of water and you spill it on the floor and leave it for one day, next day when you come back, it's all going to be gone. So what is the difference between storing water in a bottle and spilling it on the floor? What's different about it? Hold on. Yeah. Anyone? What is different? What is different about storing it in a bottle and spilling it on the floor? In terms of like what we have seen here in the note. Okay. Two participants raise hand. Yeah, Anya?
When you spill it on the floor, there's more surface area for it to evaporate.
Exactly. There is more surface area. I think Enara probably had the same. Yeah. So the surface area affects the rate of evaporation. No? Then, okay, let's say if I repeat that experiment, spilling water on the floor and leaving, in England and in Abu Dhabi without AC, right? Which one would evaporate faster? Obviously, the one in Abu Dhabi, right? Because without AC, it's so hot. So, what is the factor that is affecting the rate of evaporation there? Atmospheric temperature, isn't it? Then, what about windy day versus non-windy day? If you take a windy day and compare it with a non-windy day, yeah. I think you can all agree that evaporation would be more on the windy day. Anyway, okay. So let's write factors affecting, have a look at the text tool. Factors affecting evaporation. Number one is, hold on. Number one is the exposed surface area. More surface area, the more the exposed surface area, the more opportunities are there for high energy particles to escape, right? Then also temperature. The hotter it is, the more energetic the particles are. So you see, particles absorb energy from a warm atmosphere and increase their kinetic energy. Particles absorb heat from the surroundings and that increases their kinetic energies. All right. Particles absorb heat from the surroundings and that increases their kinetic energies. Now, so the more kinetic energy they have, the more probability. So the more kinetic energy there is, the more probable. Now probability means, do you know the meaning of probability, guys? Like when you are predicting the chance of something happening or not, you use this word probability. If something has a high likelihood of happening, it has a high probability of happening, right? And the reverse also you can understand, right? The probability that particles will leave the surface is higher. There's a higher probability that the particles leave the surface. Okay. After this more particles, huh? Okay. Then after that, we discussed that the wind conditions also affect, right? Wind conditions. Right. The more wind there is, the higher the rate of evaporation. Right? This is because the wind wait, hold on, there's a chat. I'm waiting for the chat to load. So whoever sent the message, if you can say through mic, it's much faster. It's not loading instantly on my screen. Let's just see again, chat, come on. Yeah. This is because the wind picks up so you can imagine that hold on. Now at the surface of the water, so this is related to the wind thing. At the surface of the water, let's say there are some particles, hanging around, just waiting for the opportunity to get enough energy to get out, right? So if one of them is, kind of unsure in the middle, if the wind, if the air molecule comes and hits it, then let me just draw that with a different color. Okay. So if the air molecules come in like this and hit these particles, they can pick up the water from the surface. Let's the eraser. We just erase this thing, it's kind of stupid. Right? The wind gives kinetic energy to the particle and picks it up and takes it away. We'll write that. The wind gives kinetic energy to the particles and picks them up, carrying them away.
Sir?
Yeah.
Isn't this a good thing because we want the water to evaporate and the wind is basically helping the particles to come out?
It could be a good thing or a bad thing. Now, right after this, I'm going to discuss evaporative cooling, the concept of evaporative cooling. So in that case, back in the day when people didn't have fridges, they used to use 2 clay pots in a very creative way to preserve food. Okay, in that case, you want evaporation to happen, right? On the other hand, then let's say if you are the owner of a salt flat, where they make salt. So they let the seawater into these large areas and let the water evaporate, leaving the salt behind. In that case also, evaporation is good. There are some few cases where evaporation can be bad. For example, let's say, no, just hold on, will you, till everyone writes a note. Then after that, I'll explain properly.
Okay, sir.
Okay. How are we with the note writing? Anyone still writing? No. Keshan is still writing.
So can you keep the stuff in purple, like that diagram thing, please?
Sir, what's shown in the diagram?
Sorry?
So I don't really understand what's drawn in the diagram.
In the diagram. Okay, what happens is now, this earlier we discussed that how the water molecules are always moving around, right? Moving around, and some of them have more energy than others. That part you understood?
Yes, sir.
That means the energy is not equally distributed within the water molecules. So now the high energy ones will leave on their own, but let's say the ones which have enough energy to come to the surface, but let's say there are water molecules. Wait, let me just label them, then it will be more clear. Okay, hold on. These are water molecules. And the blue ones are air molecules. These ones are, it's a line size. These ones are air molecules. So what happens is, now let's say there is some water, if there are some water molecules which are energetic enough to come to the surface, but not energetic enough to leave, then you can imagine when the wind comes, these little wind air particles will collide with this water particle, giving it enough energy that it can escape. Did the internet go? Something happened to the power. Hold on. Can you still hear me?
Yes, sir. Yes, sir.
Okay, thank God. All right. So when the air molecules come, this is like, you imagine little like balls of energy, right? So when it comes and collides, that means hits against the water molecule, it will give it enough energy. Just like, a football player kicks the football up, like that the wind is coming and giving energy and picking it up, sending it away. Now do you get it, Keshani?
Yes, sir.
Yeah, it's exactly how a footballer kicks a ball and picks it up to throw, as in kick it up, right? Kinetic energy transferred to the football in this way. The kinetic energy of the air is transferred to the water molecules and it's taken away. Right. Now everyone's done writing? Yeah? Anyone still writing? Because I'm about to erase this.
Sir, I'm drawing.
Drawing. Good that you said before it was too late. And these are just labels, so we'll make them thin. I'm just going to make them thin.
Okay, sir.
All right. Then, oops. Now let's discuss evaporative cooling. That's like a topic kind of thing. No, subtopic under evaporation. Evaporative cooling. Now, here's the main thing. If you know what the average is, no? For example, now don't write this, okay? This is just to, in case your math, in maths, if you haven't covered the concept of average. Now let's say we're adding 5 numbers, right? 3 plus 2 plus 5 plus 4 plus 3. Now, if you have these 5 numbers, 3, comma, this should be comma. So if you have these 5 numbers, how do you calculate the average of them? You add them and you divide by 5. Are you familiar with this idea? Can I have any response, please?
Yes, sir.
Familiar, no? Okay. Then, so you add them and divide by 5. So what is the answer you get? Just don't write it, just try it in your calculators. 3 plus 2 plus 5 plus 4 plus 3. Right. That's divide by 5, you get 3.4. All right. Now, imagine if I was to take some of these numbers and reduce them or remove them, the most energetic ones. Right. Now, imagine these are water particles and these are the values of their energies. Now, if I remove the most energetic one, then I'll be left with only 3, 2, 4, and 3. You understand that? Now, imagine these are the energies of the particles. I have 5 water particles with 5 energies. And I remove the most energetic one because that's the one that will escape by evaporation. What is the average of these? Can you calculate? That's 3 plus 2 plus 4 plus 3. Divide by 4 this time because there are 4 particles. Okay, what's up in the chat? Okay. Jesus. Hold on. All right. Yeah. This answer becomes 3 plus 2 plus 4 plus 3. Divide by 4. Yeah, you get 3. So, how did that happen? Right? Now, by removing the most energetic one, you have reduced the average energy. I just wanted to show you before we actually write the note, right? What's up with this? Is this annotation? Oh man, it is. Okay. So the main thing is when the most energetic energetic particles are removed by when the most energetic particles are removed by evaporation, the average energy, what's up with this chat? Hold on. The liquid is lower, right? Now this is the average kinetic energy. Yeah? So when the average kinetic energy is lower, the remaining liquid is cooler. I hope you got that, right? So now this is exactly why your body sweats to cool down, right? I can't see the chat, okay? Whoever sent the chat, my chat window is not loading, so you better say it on microphone. Okay, when the most energetic particles are removed by evaporation, the average kinetic energy of the liquid is lower. When the average kinetic energy is lower, the remaining liquid is cooler. So let's see how this is applied in different situations, right? Hold on. Second, please. All right. So let's draw. Now imagine if there's a person here. I mean, just draw a normal fellow, right? When the body is warmed up, when the body of an athlete when the body of an athlete is warmed up, the body releases sweat, right? That's something that our bodies have learned to do, right? The sweat evaporates. The sweat evaporates, and the most energetic particles leave first, no? Which makes the body have less average, or rather, which makes the remaining sweat. Guys, give me a second. All right. Okay. Which makes the remaining sweat have less energy. most energetic particles leave first, which makes the remaining sweat have less average energy. Therefore, the skin and the body are cooler. Right? Now we are almost at break time, so there's just one tiny bit more. You know, in Sri Lanka, we have these traditional water storage pots which are made of clay. So there are also this evaporating cooling can happen. So this kind of water thing with a small lid, right, made of the same material. So water actually goes like permeates through. Water permeates through through the clay pot and evaporates on the outside. Evaporates on the outside of the pot. All right. And evaporates on the outside of the pot, leaving the remaining water cooler. This is all natural cooling, right? That's it. Write this down and we are done for today.
So if we're done copying that, can we leave?
Yeah. After you're done copying, you can leave.
Bye, sir. Thank you.
Bye-bye.
Bye, sir. Thank you, sir.
Come.
Thank you. Bye.
Thank you, sir.
Welcome. Bye.
Bye, sir. Thank you, sir.
Bye. Sanut and Sandanaki writing. Probably Sandanaki is writing. No? It's okay. You can write. No issue. Sadhanaki, can you confirm that you are still actually in the class? Or is it just on? Either way.